Ah oui. Bien, bonjour à toutes et tous. Alors, nous sommes le 4 septembre 2025 à 14h30 et c'est l'heure de procéder à l'habilitation à diriger les recherches, la soutenance, à écouter la soutenance de l'habilitation de Miguel Montarges pour diriger des recherches à l'Observatoire de Paris-PSL. From now on, I will switch in English because one member of our jury is an English-speaking member. So we will do this all in English. We have several members in the jury. Anna Palacios, who is an astronomer at University of Montpellier. Céline Raylet, who is online and who is an astronomer at Besançon Observatory. Philippe Stay, who is a research director at Lagrange Laboratory in Nice, Fabien Baron, who is a professor at Georgia State University, and Alex de Cotter, who is professor at Anton Pannekoek Institute for Astronomy in the Netherlands. So we will proceed as follows. First, Miguel will make a presentation of about 55 minutes about his research and his vision for the future and his research theme. Then the jury members will ask him questions, starting with the jury members who are online, and then we will move on to the jury members who are in the site. Then we will close temporarily the public session, so the jury will move out to another room to start the deliberations, and we will come back no earlier than 5:30 probably to give the result here. So there will be a second public session a little bit later in the afternoon. I think we have said all there is to say, so Miguel, you have the floor. You have 55 minutes to tell us what you have done and what you plan to do.
Thank you very much, Vincent. So it's a pleasure to be here. Thank you, all of you, for being there, here and online. So I'm going to present you the research I conducted for the past 11 years on cool-level stars, and as Vincent said, some vision for the future. So this is the outline of the presentation I will follow, a short introduction to get into the field. Then we see the problematic of triggering the wind of red supergiant stars. In the third part, the problematic will be how to form the dust in the wind of cool-level stars. And the final part will be how to shape the mass loss and to see the importance of binarity, and then a short conclusion. So first, the introduction to see what I have been studying. So this is a sketch of stellar evolution with, of course, approximations, and the main one being that the star is a single star and there is no interaction. On the horizontal axis, we have the time, and on the vertical axis, it's the increasing initial mass. And here we have two pathways that are going to be of huge interest for us. First, well, what is going to happen to a sun-like star? So the star is born in a nebula and is formed a protostar. Then it becomes a yellow dwarf, like the sun. And after several billion years, it will evolve toward the red giant phase and the asymptotic giant branch phase, eventually forming a planetary nebula, and then a white dwarf. And for more massive stars, above 8 solar masses, there are blue giants. Some say blue dwarf, but it's also used for another part of the stellar evolution. Then a red supergiant, and then it becomes a bit more complex, meaning that the star can directly explode as a type 2 supernova and form a neutron star or a black hole, or it can evolve back to the blue, that's the blue loop, and explode as a supernova in the blue stage, or in between, or even come back again to the red. And all this depends on the rotation rate of the star and on the mass loss rate of the red supergiants, which is important to characterize. And of course, there are many other possibilities, some that are not even on this sketch, but I don't think there is a sketch with all the possibilities, actually. And I'm focusing on these two parts, so the red giant and the red supergiant phase, so the cool level state where basically the star is big and red. So in terms of quantitative meanings, in what we call the HR diagram, the Hertzsprung-Russell diagram, so here we have the temperature of the star, cooler in the red and hotter in the blue, and here the luminosity. And the diagonal, the main sequence, represents the main stages of evolution of the star when it is burning hydrogen into helium. And at the end of their life, stars will always evolve, at least between 0.8 and 35 solar mass, toward the upper right part, where they become red, cool, and luminous, meaning big. So we have the AGBs there, and the red supergiants there, with the final evolution stages. And now this was a theoretical diagram, and here we have the observed diagram with some stars that are well known because they are visible to the naked eye on the upper part, some that are less famous here in the less luminous part, and some stars that I'm going to talk about, of course, Montarges, and as you all expect here and online, Recherches. The two types of stars are summarized here with some values to really show that they are similar in appearance, but in reality quite different. So for asymptotic giant branch star, so below an initial mass of 8 solar mass, their radius is between 300 and 500 solar radii, which means 1 to 2 AU. Luminosity between 1,000 and 10,000 solar luminosity, and they are pretty cool between 2,500 and 3,500 K for the warmer stars. And here is the result of radioactive hydrodynamic simulation conducted by Glenn Freitag and Andra Cavassa that shows what the star would look like with dark patches and bright area. And now for red supergiants, much more massive, more than 8 solar mass, up to 35 solar masses. Much larger. At this time, this is between 500 and 1,500 solar radii. So this is basically the size of the orbit of Earth. This is the size of the orbit of Jupiter. So quite impressive, much more luminous and a bit warmer. And this is now the result of the simulations. More convective cells, more patches, and of course, I'm going to show the movie here of two types of stars. And here we see, I think, more apparently, the difference between the two types of stars. So here we see mainly convection for the surface of red supergiant, while here for AGB stars, there are also radial pulsations. So the size of the star is changing over time. And I defy anyone to try to draw a circle to define what is actually the photosphere and well, the surface of the star, while it is perhaps a bit more easy for the red supergiant. To stop, because otherwise we are going to spend 1 hour on this movie. And we could wonder what is the interest of studying cool level stars beyond their main interest by themselves. They have consequences for other fields of astrophysics. First, the most obvious one that we say each time is that they enrich the galaxy and the universe in heavier elements. So basically, most of the elements that we see on the Mendeleev table are coming from directly cool-level stars or the ultimate stages that follow the cool-level stage, meaning compact objects. They are also shaping the interstellar medium. So this is the Carina Nebula. So this is a vast complex of gas and dust in the southern hemisphere. And all the shapes here are mainly created either by the wind of multiple stars, but also by the explosion of supernovae. And because there are a lot of massive stars there, there have been in the past a lot of supernovae explosion in this region. Also, red supergiants are the progenitors of supernovae. and compact objects. And basically, the way we perceive the light curve of supernovae directly depends on the amount of mass that has been lost by the red supergiant and also in which direction. And the final mass of the star depends on what has been lost here in the coolable state. So for some stars, the fact that it will become either a neutron star or a black hole depends on what happened during the red supergiant branch. And basically, the progenitor gravitation waves depends on what happens here. And finally, I will also mention that we observe exoplanets when stars are being formed during the main sequence, and rarely when stars are dying. But it seems that they may have an impact on the star. So it's also interesting to look for exoplanets around coolable stars. So the main question I'm trying to answer to in my research are those ones. So first, for red supergiants, how do we trigger the wind of red supergiants? So we see that there is a star. There is an envelope of gas and dust that comes from the star, but we do not know how the material is leaving the photosphere here. So what is happening in this small region close to the surface? We don't know either how to form dust. So here we have dust forming, here another artist's impression. We do not know how to go from the solid, so the gaseous phase, gas, to the solid phase, dust. And finally, a lot of stars are binaries. A lot of stars are hosting planets. And what is the consequences of having another object orbiting a big red star? And what are the consequences for both objects? Actually, you have the beginning of an answer. To study this, well, we need to look at the circumstellar envelope of the star. So this is a sketch again with the photosphere, so the star itself. The first region where we have many gas and only the precursors of dust. Then here it's where dust is really forming and the wind is being accelerated. Then the wind has reached a constant velocity, but we start to have a photochemistry from the short wavelength radiation coming from the interstellar medium that can photo-dissociate the wind and the gas. And well, to look at this region from Earth, for most stars, we need to go beyond simple single telescope use. We need to use high angular resolution. So when we want to observe the photosphere, which is the inner part, well, we usually optical interferometry or spectropolarimetry to see the formation of the first dust grain in the inner singular environment. We can use direct imaging with adaptive optics, for example, at the VLT. And actually for the accelerating region, photo-dissociation region, but also for the entire circumstellar environment, sub-millimeter interferometry with the ALMA or NOEMA observatories are the best tools for looking at those regions. And I've used all this. That's what I'm going to show you now. First, also a short look at the sample of stars. So the idea is to look into detail in the surface and environment of stars. So we need to look at stars that are nearby and that are large in the sky. So this is a map of red supergiants in the sky of our planet, and only red supergiants. So we see the imprint of the Milky Way with the two Magellanic clouds here, and the size of the dots corresponds to the angular size of the star. The color shows what tool we can use to see the photosphere and the environment in the optical domain. In orange, so we have two stars in orange, the two red supergiants for which we can obtain an image of the photosphere directly with adaptive optics right now. In blue, stars for which we can get an image of the photosphere with optical interferometry. And in red, stars for which we can get the diameter from optical interferometry. And in black, we cannot really get anything. This plot is going to evolve in the coming months, actually, with the upgrade of the Shara facility that will be able to observe, again, big stars that currently myself is here in black because we cannot observe it. In the future, it will be in blue. And now the same map for red supergiant. I forgot to mention that there are some stars that are mentioned that I'm going to detail in the presentation. And here for the AGB stars. So the Milky Way is less visible because the stars are much more numerous and also closer when you want to observe them with the same color code. And the star that I'm going to mention in the presentation is Pi 1 that is here. Ardor is the closest, but I'm not going to talk about it, and L2 puppies, but I will not have the time to go over this, even if I worked on it a bit. I'm jumping now to the first part of the presentation after the introduction. So let's look at how to trigger the wind of red supergiant stars. So the problem here is that when we see red supergiants, we see a star. This is a direct image of Betelgeuse with the sphere instrument at the VLT, so with adaptive optics in the visible. And this is the environment of the same star with the VCR instrument at 10 micron in the mid-infrared. And here what we see is the thermal emission of dust. And the small dot at the center is the photosphere of Betelgeuse. So it has already expelled all this material. It comes from the star, but we do not know how to make it escape the photosphere. So to better constrain the mechanism, or try to at least identify what they could be, I've been studying this star, some others, with high angular resolution. And this is one of my results. It was in 2016, but the image is from 2014, where we see a bright spot on the image of the surface of Betelgeuse. It was observed with Pioneer. So this is a model image, the best fitting model of Betelgeuse in the H band at 1.6 micron. In parallel, a few months later, we had observation with Sphere. It was actually among the first programs executed on Sphere when it was installed with adaptive optics. And what we see here is polarization. So the star here is normally the red circle. And what we see is light polarized, meaning scattered by dust in the environment of Betelgeuse. So this is a cloud of dust. Here it's again the photosphere, this time in the sub-millimeter domain with ALMA in the continuum. And another result I participated in, it's this time the molecular envelope of Betelgeuse, but we see the velocity of the gas. And we see that one side is moving towards us in blue, and the other side leaving away. So the star is rotating this way, at least the envelope, but also the star, are rotating this way. And the conclusion developed here in this article, based on all these results, is that this is the polar axis. So all this happens on the north pole of the star. And we hypothesized that the polar region, the northern region of the star, could be a privileged region to form giant and persistent convective cells that could expel material in that direction. So that the convection could create material expelled from the star. And this is what is actually explained in this image. And we call this kind of convective cell raw convective cells because they could be persistent in a particular region. Now I'm moving towards another star to try to better constrain the role of convection in the mass loss. This is going to be Montarges. So we see the convective pattern in the simulations. We have seen it in several reconstructed images from optical interferometry, but yet the simulations cannot yet launch the material. When we have the movies, as I've shown you, all the material is falling back onto the star. So we need to add an ingredient in the simulation. And the idea is to look into better detail at the convective pattern to try to find this missing ingredient. That's what I did in 2017 with Pioneer again. So it was a VLTI observation of the red supergiant Montarges. So these are the squared visibilities that gives us basically the size of the feature on the surface of the star. And the closure phase that tells us about the asymmetries on the surface. And normally when we do optical interferometry, well, we stop the observation for regular stars to the second or the third lobe at best. Here with Montarges, because it's really huge, with the Pioneer, we were able to go up to the 16 lobe of visibility, meaning details on the surface that are about 1/16 of the angular diameter. So that was the unique time we were able to probe really small detail on the surface. And basically, the observations are best reproduced by random distributions of convective bright cells between 0.05 and 0.45 stellar ready, which is not what is present in the simulation. So clearly, this kind of tiny, small convective cells are not present in the simulations, probably because of numerical limitations. And that could be a reason that we have this missing structure in the simulation, that we cannot launch the material. Because they are present, they are real, they are giving energy and turbulent velocity inside the photosphere that could levitate the material. Something else we've been working on has been to, well, try to follow the connection, because we see it, we see the small details, but is it persistent and how is it evolving? All red supergiants are semi-regular variables. So this is the light curve of Recherches between 2015 to 2023 in the V band. And well, we see this, the short variation associated to a pulsation, and also a long secondary period that I will discuss a bit later. And we have no idea what it means for the star to be dim, to be bright, to be in the transitory region. We have no idea what the star looks like as its magnitude, its luminosity is changing, which is not the case for a GB star. We know that they are pulsating. So we would like to have this kind of image during the pulsation cycle of a red supergiant. But it is not possible, because to obtain an image in optical interferometry, we need to multiply the baselines between telescopes. And this is done at the VLTI by moving the telescope on a scale of a few weeks. Problem is that the star is going to evolve in this time scale. And also at best, there is, I think, one imaging slot per semester at the VLTI. And it's not enough. We need continuous imaging almost to be able to say something about the evolution of the convective matter. So do we give up? No. There are other ways to look at the surface of those stars. So this is the Pic-du-Midi Observatory in France. And this is the TBN, the Telescope Bernard-Hinault, where the team, led initially by Michel Aurière, and now it's Agnès Lèbre, Arturo Lopez, and Philippe Mathias, are observing evolved stars with polarimetry. And this is what they have. So this is a compilation of several lines. So the least square deconvolution method to get a better signal-to-noise ratio. This is the intensity in a line, in several lines actually, in 2013 and 2014. This is the polarized signal. So we are interested in the red and blue for the linear polarization. Green is circular polarization, so magnetic field. And here it's the test signal to check that everything is at zero here. And from here, this polarized signal, so linear polarization, the team in Toulouse was able to reconstruct on this star, so it's not Betelgeuse, it's CE Tauri, another red supergiant, an image of the surface from the linear polarization signal, where we see a bright spot, some dark area. This is interesting, but when we see that, we wonder, is it real? Because apparently there is no way to test that the method is indeed reconstructing an image that is real. Luckily, actually it was not luck, but we had observations simultaneously coordinated at the VLTI on this particular star to do precisely that. And this is the reconstructed image of the surface of CE Tauri at the same time, December 2016. And we recover the bright spot here and here, the two spots, the dark area there, and the other in the northeast region. And the two images were reconstructed independently. So we were quite confident that this was quite real, but also myself, I was quite happy to see that we were reaching something similar in optical interferometry. And the idea is that with two different observables and reconstruction methods, we cannot both be wrong the same way. So this is only what the star looked like. And they continue their work, and now this is Betelgeuse, observed between 2013 to 2018. So there is a way to get time monitoring of the surface of red supergiants with a combination of polarimetry to get these nice images, but optical interferometry is still used to properly orient the image and to recover the exact size and contrast of the features on the surface, which is important to feed the convective models. And since we have been talking about exotic ways of imaging the surface of a star. This is something that I did in 2023 and that I'm still working on actually. The paper is in preparation. So again, Betelgeuse. I don't know why always this star, but the 12th of December 2023, an asteroid of the solar system called Leona passed exactly in front of the star in this pathway that started in the Middle East, went over Greece, Italy, the south of Spain, and Florida. And actually, there are some people in the room that were here in the south of Spain during that famous night, where there were clouds everywhere. But we managed to get some observations. So these are the stations. So we had amateur astronomers doing the observation because there are no 8-meter telescope to observe Betelgeuse and Leona on this path. And the idea was to collect the photometry, so the light curve of Betelgeuse during the event. And what we see here is the imprint of the occultation. So when Betelgeuse did not disappear, it went dimmer, but it was too big to be hidden by the asteroid. And we see several light curves. Some are good, some are not so good. Here, it's not multiple occultations, it's clouds passing in front of Betelgeuse, also here, but some are pretty good. And so we are currently working on reconstructing an image. I was hoping to show you the image. The problem is that so we have preliminary results, but we got a new light curve in July that we are sleeping somewhere for a year and a half. And since also we are targeting nature because we have already the green line from the editor, and since we are on YouTube, I cannot show you the images that we recovered, but they are definitely the best images of the surface of a star, thanks to this unique method that was used that night in Spain in December. So going to the other subject, sorry for the teaser, I know it's frustrating also for me. So now I'm moving towards the projects, what I will do in the future, and there is something that is very hot and very immediate, is again Miguel. So I said that we had this result from 2018 where we had the rotation of the star. So this way, and I didn't mention the rotation period, it's 30 years. So it's not a fast rotator, but still it's close to critical for a size of this star, and it's definitely too fast. So people have argued for a long time that it was the signature of a past merger. So that Betelgeuse had engulfed a companion that had spin up the star. But there was a paper in 2024 saying that this is not rotation that we see. It is the imprint of the convective pattern. And by chance, it looks like convection. So an upwelling cell here and something going down. Okay, so I think what we should do is relatively fast, trying to observe the star again to see if we still have the same pattern or not, because it's important to define the evolution of red supergiant and of this star in particular. But last year, there was this results where Goldberg et al. Looked at the light curve of the star and the radial velocity across time, and concluded that the long-term variation over 5 years was caused by the presence of a companion that was a photo-dissociating dust around Betelgeuse. And basically, when the star was brighter, it was because the companion was in front, removing the dust in the line of sight. And when it was moving away, dust was coming back, and the star was dimmer. Interesting, they made the prediction with a maximum elongation in December 2024. And in July 2025, so this month of July, after I submitted the manuscript, there was an announcement that the companion of Betelgeuse had been found. So this is Betelgeuse, this is the companion, and this is the press release image from the Gemini Observatory and Noir Lab in the US. So quite convincing, except that this is a press release. Actually, it's an artist impression. The real image is here. So this was what was observed, the reconstructed image. So we have the red supergiants, and we have here the companion. And something else here. They say that this is not real because they have what we call in interferometry the bispectrum that allows to remove this, and the real one is this one. This is just an artifact. But this is a 1.5 sigma detection, which is a bit weak, let's say. Normally, we should claim detection at 3 or 5 sigma, but maybe real. So I think it is now very important to determine if there is a companion around Betelgeuse, to understand the rotation of the star, its ephemeral status, has it interacted before, is it going to be a merger in the future? Plenty of questions. So the next maximum elongation is in 2027. So we have time to get a reference image and a test image for the companion. We'll see. Now moving toward the work of my last student, internship student in a master's, Lucia Mel, who is in the room. She worked on Montarges with the gravity instrument at the VLTI. So these are the data she was working on. So we have square visibilities, closure phase, and here the color codes the wavelength. So a very rich data set in the cable with continuum and the molecular line data. And from this observable, she was able to reconstruct images in the different spectral channels. So here we have an image in the continuum. So this is the spectral profile. The first image is in the continuum, and then we are in the spectral line, in the blue wing, the center line, and the red wing. And we see that the star and the environment are evolving. So we can have information about the composition of the environment, but also the velocities, because we are looking inside the band. And this is the kind of map that we are aiming at. This is called the moment one map. This is coming normally from the radio sub-millimeter domain, where we combine all the images in the band to form a velocity map of the star. So this is still preliminary. We still need to refine the reconstructions and the weighting of the images for the moment one map. But ultimately, we hope to be able to get a velocity map that will tell us about the motion of the material just above the photosphere of the star. Again, to study how the wind is launched from the photosphere. And I'm back here on the visibilities. The problem when we do image reconstruction with visibilities and closure phases is that we have to give a priori information to the algorithm that is going to go from this to an image. And here, for example, it was that we want the pixels to be grouped towards the center because we have a star and not a diffuse cloud. But Fabien Baron, who is online in the committee, is working on ways to avoid having this biased a priori by using artificial intelligence, so neural networks trained on typical astrophysical objects, so here YSOs, young stellar objects, and a test network trained on a rectangle. So basically, the neural network is trying to reconstruct either YSOs or rectangles from visibilities and closure phases. These are the steps of the training, so this is indefinite, and in the end, we have YSOs for the first network, and for the second, we are training it to reconstruct rectangles, and we have nice rectangles at the end. Now on a real data set with visibilities and closure phases that was published in 2023, this is what was reconstructed by a classical algorithm, Squeeze, also developed by Fabien Baron, the YSO. And now what is reconstructed from the neural networks? The one on YSOs, trained on YSOs, quite similar, and the one trained on rectangles. And what is really interesting here is that even with rectangles, instead of having a weird rectangle all over the image, we recover the ring of the YSO and the white spot. That shows that the neural network is not so much biased by the a priori information of the training compared to here, where we clearly say we have a ring and we have this kind of object. So this is a way to reconstruct perhaps images that are less biased, and this is something that we want to explore in the future to have better image reconstruction, so for AGBs and red supergiant star, using simulations to train the network and also archive data. And I'm certain that Lucy, during her PhD that will start in October, will want to work on this topic in particular. And then, on the long term, there is the future of internet. So there has been several discussions for the past years on what we do after 2040. So currently we have the VTI, we have SHARA, and there are several pathways that are explored. So more telescopes. We're not sure of the size, ATs, UTs, EITs, so 2 meters, 8 meters, 40 meters telescopes. Do we want longer baselines to have better angular resolution, an interferometer in the visible, a better spectral resolution? We're also running after sensitivity. So I'm not going to say here what I want because, well, I would like longer baseline and more telescopes, but it also depends on the will of the entire community. There have been several propositions and artist impression. This is mine of what I would like. Perhaps this is not totally realistic. I know that there have been some sketches that were not totally realistic, but this is one among others. And the nearby future is well, the EIT. So these are images from this year, the dome in construction and the telescope. And of course, there is a big telescope of 39-meter diameter. My first idea when I see that is to say, okay, let's point it towards Betelgeuse, because it's time there is a new telescope or a new instrument. We try to observe the brightest and the largest star in the sky. Actually, Kina Nasquadra, during his M1 internship last year, worked on preparing the strategy of observation of Betelgeuse with Mikado, the first light instrument. The first question was, is it feasible? The answer is yes. We can point a 39-meter telescope on a -4 magnitude star in the infrared, and we can see details on the surface. And then the question was how to time the observation to properly sample the evolution of the convective pattern. And we saw that between 2 weeks and 1 month, between the 2 images, we were not missing any evolution of the convective pattern, at least according to the simulations. Now I'm going to move towards forming dust in the environment of coolable stars after this project on imaging the surface. And here, the problematic is that we know that we have gas in the environment of coolable stars, simple molecules, and to form dust, we need to assemble these bricks to form a complex structure moving from gaseous phase to solid phase, which is easier said than done. And this dust structure has implications for shaping the environment and accelerating the wind. So how do we go from here to there? Well, again, I'm going to talk about my favorite star, Betelgeuse, and I think you know about this subject. This is the light curve of Betelgeuse between 1980 and conveniently 2018, and we see the variation with time of the luminosity. And as you know, in 2020, this happened. So this is the great dimming of Betelgeuse, something that has never been observed for 200 years that we have been monitoring this star. And a lot of people were wondering what was happening to Betelgeuse because it was visible to the naked eye. And you could see Orion in the sky in winter and see that something was wrong, definitely. And some people, particularly in the US, said that it's about to explode as a supernova. And, well, I did not believe this. And we used a sphere at the VLT to image directly the surface of Betelgeuse with adaptive optics. And these are images between January 2019, so a year before. Luckily, we had the observation from that time. Then at the beginning of the dimming, at the deepest of the dimming, and during the recovery. And the conclusion of the article was that what we were seeing was a cloud of dust formed by material expelled from the star few months before, and a cooling of the photosphere. And the main conclusion was that we had a cohabitation of a cooling of the photosphere and the cloud of dust. So we witnessed somehow dust formation in the environment of a coolable star, except that this time it happened in the line of sight. And Emily Cannon, who was my PhD student at that time, and who is also in the room, worked on the Matisse data of this event. So Matisse is using the VLTI in interferometry in the mid-infrared to see the dust at high angular resolution. And here we have the squared visibilities and the closure vessels. So this was a very complex data set, because ideally with that, we would like to reconstruct an image, because it's very difficult, if not impossible, to properly model this, because it depends on the geometry of the structure. But Emily managed to demonstrate that the signal was compatible with the presence of dust in the environment, and in particular in the line of sight, but that there were probably and most certainly clump of dust around the photosphere, at least 2 to 3, even perhaps more, to reproduce this kind of complex signature. Normally, again, we should have reconstructed an image, but we had only this observation because we were in a DDT, so director discretionary time, and so we could not recover more UV points to reconstruct an image. Again, the dimming of vintages, so this time it's Edwige Leserve, who did her internship last year during her bachelor studies. She's also in the room. So this is, we saw actually the same observation than the nature paper, so the dimming paper, but this time it's polarized light. So what we see again is cloud of dust around the vintages through time. So before the dimming, at the deepest of the dimming, and afterwards. So the star is the black disk at the center, but here we are interested in dust, not on the line of sight, but on the sides. And Edwige managed to reproduce the polarized signal using the code, the relative transfer code RMC3D to obtain this cloud of dust. It's quite exceptional because she managed to do that in 1 month. That was the time of the internship. And she managed to deduce velocities, tangential velocity of the cloud of about 8 to 15 kilometers per second, which is totally consistent with the velocity of the gas on the surface of red supergiant. So indeed, we may be seeing a cloud moving away from and on the same topic, this time on Montarges, Emily, during her PhD again, her first article, used data I obtained on Montarges. This is the polarized light on Montarges with the green circle showing the size of the star. So we have a cloud here on the southern part and on the northern part. And Emily reproduced the polarized emission with MC-Max 3D, another radiative transfer code, during the first years of her PhD. And it was a very detailed study because she had to start from scratch. And it was the first time that we were doing this in polarization. And she studied in detail the composition and the size of the dust grain, and most importantly, the morphology and the position of the dust in the environment of the star. And the conclusion was that of all the studies is that we have dust forming very close from the photosphere of red supergiant, closer than we imagined, so at higher temperature, meaning that we have to find a particular dust species to form that close to the photosphere. And the chemical pathway to form this dust is quite uncertain. So we need to have more work on the chemical network that are being developed to understand the pathway to dust formation. Then I'm mentioning results obtained during the internship of Aisha Hashimekova, who is now in a PhD at LTE in Paris Observatory. She did that 2 years ago during her M1. So Pierre Kervella, my former PhD supervisor, published this result in 2011 of the environment of Betelgeuse with clump of dust identified around the star. And we had observations obtained later, and Aisha was comparing, doing the reduction and analyzing data, and then comparing the two data sets by doing here an image difference to see the motion of the clump around Betelgeuse, the dust clump. And she managed to have a tangential velocity between 11 and 20, so kilometers per second. So higher than what we had closer to the star, which is normal because here the material has been accelerated by radiation pressure on the dust grain. So let's look now at the future, what we could do with dust. So, well, the first idea would be to use the GWST, now that we have it in space, with MIRI, to look at the thermal emission of dust in the environment of Kuiper star. Usually, for stars that are large enough to do that, it's not possible. because they are too bright to be observed with the GWST. For example, people have told me, intelligence with GWST. The answer is no, it's not observable. But we could use Matisse to look in more detail in imagery. We don't have proper image reconstruction yet in the mini-infrared for cool stars. It will be quite a challenge to identify the location of the first grain of dust. And in the future, in the coming decades, we hope to be able to use Matisse as the ELT to do precisely that. So we need to identify the location of dust, the first grain of dust, to identify clearly the species that are forming, and to work well with people doing a laboratory experiment, for example, in the UK and in the US on this subject, and also with the people doing the chemical networks, for example, in Belgium, to understand how to form the first grain of dust from the gas. And now I'm moving toward the final part on AGB star, so shipping the mass loss. Again, the problem is relatively simple. So we have planetary nebulae, which has the final stage of evolution of solar-like star with a white dwarf at the center. Yeah. So we have plenty of shapes of planetary nebulae, quite different. But at the origin of those planetary nebulae, there is always an AGB star that is more or less spherical, but that is very different from something producing a bipolar jet that we have here or here, bubbles. We have plenty of structures, but from the start we have something spherical with material moving in all directions. So what is happening to the wind to be able to observe this kind of structures? Well, when I was in postdoc in Leuven, we selected 17 cool stars to be observed with ALMA, oxygen-rich. And the justification of the proposal, I remember that clearly, was that they are simple laboratories to understand the pathway to dust formation. Because we have an environment that is normally spherically symmetrical. There's nothing to induce a disk, for example, like in protoplanetary disks, which are much more complex with planets forming inside. Cool star is just gas and dust moving away radially. Of course, we were wrong. When we observed those stars with ALMA, so the 17 stars, we saw plenty of structures. So here the color codes the displacement on the line of sight. Blue towards us, red away. And we have plenty of structures. So these are the signature of angular momentum added in the environment of AGB stars. And these were the signature really of unknown companions, stellar, substellar, around those stars. It was a paper in Science in 2020. And I focused over the past 2 years on a particular star, Pi-1 Group, because the ALMA continuum showed this. So the red giant and something else on the side, companion. So we had this information in 2019. We had the displacement, the proper motion of the star in 2016 from Gaia and Hipparcos. And we also had the motion of the gas. So here, the black contour here, they correspond to the continuum image. The color corresponds to the motion of the gas. So the gas is in a Keplerian rotation around the binary. And here I have a slit in dashed line to produce this position velocity diagram. What is important is that the gas that is represented here follows a Keplerian law that is shown in red. So it's orbiting the binary. With these clues, I used Bayesian inference recovery code called UltraNet to obtain the orbital solution of the system. And here we see that we recover the position. So in red, it's observed, in blue, it's predicted. Here we have the proper motions that are aligned with the right velocity, and we reproduce the motion of the gas. The period is about 11 years, the separation 7 AU, pretty far, an eccentricity that is not zero, and the companion mass of 0.86 solar mass. And that means that the companion is either on the main sequence, the K dwarf, or on already a dead star, white dwarf. And we had a way to test the solution because I had sphere observation, so the dust, again, in polarization, over time, between 2015 and 2021. This is, well, the 2019 with the continuum image. And in the yellow star here, shows the predicted position of the companion from the orbital solution. And it always falls on the head of the dust tail, showing that the solution may be exact. But something that is quite interesting is that what we see here is not the companion, because the K dwarf or Y dwarf star should not be visible with this signal-to-noise ratio in the ALMA continuum observation. What we see here is an accretion disk around the companion. And if the companion is a Y dwarf, it triggers a nova explosion every 900 years at 162 parsec of Earth. Must be quite visible. And this is a very nice prediction, because 900 years, if it has happened, let's say 300 years ago, the next one is in 600 years, no one will care if I am wrong. So it's a perfect way to do a prediction. And so the future of this is to identify, so detection, find these companions by chemical differentiation. So if the companion is hot enough, we can see the imprint of the companion in the gas from the proper motion anomaly, from the effect on the mass loss, and sometimes by direct detection, particularly with the HWO in the long-term future. But we need to find this to see again how stars are interacting at the end of their lives and how it can change the evolutionary pathway and how to shape planetary debris. We have an ANR in preparation on this particular topic with colleagues in Toulouse, Bordeaux, and Nice. And now I'm moving towards the conclusion. So first, conclusion, there are other cool above stars than Betelgeuse. I think it was not obvious for everyone in the room or online, and more surprising, I'm studying them also. So first conclusion. And now the real conclusions. Well, there are plenty of things to do on cool above stars. So as I said, imaging the stellar surfaces to understand how the material is leaving from the photosphere, what is the physical process allowing material to move away from the photosphere, with direct imaging, monitoring through time of the surfaces, better image reconstruction, and I am very excited to be working on that soon, I hope, and also imaging with the ELT. I can't wait to have people telling me that I'm crazy to use this stuff on Betelgeuse. Then how to form dust? Well, we need to identify, which is not clear yet, where are the first grains. We see dust close to the star, but are these the first grain? Are they closer? And what are the chemistry? What is the chemistry of dust close to the star? It's nothing but clear, and we should see also able to see the depletion of the gas with ALMA. Should show us what are the first gas species to disappear into the solid phase. And finally, well, finding and characterizing the companions to understand the interactions for RGB stars. So that was the end of the presentation. But also for red supergiants, because the red supergiants, they all should have companions, but we almost never see companions around the star because they are too bright. So we need to find them and to understand how they interact at the end of the life of the star and how it can impact the supernova or the final phases. Thank you for your attention. I will take the question from the committee.
Thank you very much, Miguel. So we will now take the questions first from the members of the committee who are in online.
I think you don't have to say
so I need to turn on, I guess, the microphone.
Céline, you need to turn on your microphone.
Sorry. Can you hear me?
Yeah.
Yes, hear you, Céline.
Yes, thank you very much, Miguel, for this very clear and nice presentation, as clear as your manuscript. It really gives a very nice in-depth summary of your work on not only Betelgeuse, but on also other cold evolved stars, and all the link with so the Maslow's process that can govern this evolution, and also the link with the initial condition on a planetary nebula and of the last stage of the star, the life of the star. And I also appreciated the fact that you use everything you can use. You show very good and extensive expertise in multi-wavelength observation, optical, infrared, millimeter, spectropolarimetry, high angular resolution. So it's a very rich research that you are doing, and also using models. So very yes, extensive study of the stars. So I wanted to congratulate you for all this work, and also your involvement in many collaborative projects. So yes, I really appreciated the diversification of all the approach you use to do this study. So I have a few questions. I tell that it's not I'm not an expert on as you know, on giant stars. I know more about red stars, but very small ones. So maybe some of my question will be a bit naive. And I have a first general question, because I'll start with this one because you have this slide, this conclusion slide. So depending on the observations you use, you will probe different parts of the stars, either the photosphere or the envelope, or even a larger size around the stars. And my question is general. I think at the end you want to have the complete picture of the stars, and you will learn different things from different parts of the stars and what you see. But how do you reconcile everything in the border? I mean, you need to have a very final picture of all the stars, from the photosphere to the very large scale.
We take some time to answer that one. First, there are not so many stars from which we can see from the photosphere to the environment. So that simplifies a bit things. And then the lucky thing that we have is that, for example, when we do observation, let's say for looking for dust, an example, when we want to look at the environment, because dust or the gas are emitting in a limited spectral region, we have always way to obtain also data from the photosphere. So it's not just we get information about the environment, but we have, for the same price, simultaneously, what is happening on the photosphere. So we can always reconnect, as you say, what is happening. So there are no clear border in the data, basically, because that we are going to have the environment and the continuum. And also then, of course, what is implied in your question, which is the great difficulty that we have had when we've been working with Agnès Lèvre, with Philippe Mathias, Tito Lopez, and Fabrice Serpin, is the coordination of the facilities. When we want to have, for example, observation at Narval to see the monitoring of the surfaces, and also a reference image at the VLTI, or seeing the dust with the VLT. Well, these are different facilities with their own schedule, their own proposal system, and it's not always possible to have observation simultaneously. And then what we do in this kind of collaboration is that, well, the first that has to submit a proposal does it on the target. And we mentioned that there are other facilities that are going to be coordinated, but there are always scientific questions to be answered to with the data set alone. And then, of course, the comparison between the data sets is mentioned as a secondary objective, even if in the end, in the article, that becomes usually the dominant part, because that's where we have the spectacular confirmation that we see the same structure on different facilities. The answer to the question in that case is that we try to ensure the connection by having coordinated observations. And coordinated means that the spacing, the time spacing between observations should be less than the evolutionary time of the structure. But that's also where it is interesting. Sometimes we see that the evolutionary time is faster than what we thought, and we still learn something. That was the case with the great dimming. It was an event that in the end was much faster than anticipated for a supergiant.
Yes, so I understand that the strength is really to be able to correlate the shape or images of different kind of observation. Is there a next step that goes to the composition of at the surface of the stars and the envelope, and to follow the chemical process that occur in the different parts? It's totally not reachable for now, but
well, for now, the chemical process, we need to reach it with ALMA by seeing depletion of the gas that is moving towards the solid phase. So that is would be relatively, well, in theory, relatively easy. And the difficulty resides in the high angular resolution that's needed. So we need the largest stars, the longest baseline, and we have then the very bad signal to noise ratio. So it's not so easy to find gas close to the photosphere. And then I think something else than composition, chemistry, to perform the connection would be, as we already did with, it was, I think, Edwige and Aisha, was with the velocity, which is something very interesting to see if we have we recover the same displacement of the feature from the photosphere towards the environment. Then we can trace an event, something that has been expelled from the star, and see the evolution of the shape, the composition, and the structure across time as it moves away from the star. Okay. And we are almost there already.
Okay, so maybe I will go just to a more detailed question. You showed the first study you showed about Betelgeuse and the potential correlation between the pole direction and the bright convective cell, and you say that you need more observation to understand what is the process behind this. What are the how can we know what is the process? What is needed to know that? More modeling, more observation.
So on the specific case of Betelgeuse, I think what we need, and I hope to submit the proposal next year, is a long baseline ALMA observation to confirm that indeed this is the pole direction, that we have the star that is rotating this way. And so the main science goal will be the line to identify the rotation. But as I said, additionally, we can have a secondary science goal, which is again the continuum image, and we see also if there is a spot at the polar region. What is a bit tricky, I think, and I'm just realizing that now in live, is that clearly the light curve of Betelgeuse, the pulsation shape, has changed since the great dimming. So in the past, the period was 400 days. Now it's 200 days since the great dimming. Perhaps because we have removed material, so the star, the resonator vibrates in a different way. It is also possible that it has changed the way convective cells are forming and the role of the polar direction, if it had a role at all. So it's true that if we find something that is different from what was observed before, it could be that the polar region does not play a role at all, but we cannot exclude that it could be due to the dimming. So perhaps what we should do, and also again improvising, we should not just observe Betelgeuse, but also red supergiant like Montarges, because it's the similar size in the sky, to see if we can identify the rotation of the star and also a particular region. Because I have difficulties to imagine that such process would be happening only on a single star.
In different parts of your work, you are using simulations from hydrodynamical models. I wanted to know how your observation help the modelers to improve their models and which part of their models.
You mean the convective simulations of Andrea?
Yes.
Okay. So first, well, there are several things. So clearly, well, with Montarges, the pioneer observation where we had the 16 lobe of visibilities, we identify structures that were not present in the model. So clearly, the convective pattern that is present in the simulation does not reproduce what is happening on the surface of stars. So there are smaller structures that should be present in the models. We also see that the size of the convective cells can be sometimes larger. So we have these rogue convective cells, as they were called by Pierre Carvela, large, bright, and persistent. And it's also something that cannot be reproduced in the simulation. So I cannot exactly tell them, okay, you have to tune these peculiar parameters in your simulation, but I can tell them that the way the convection is reproduced, the shape, the time scales, the contrast, does not correspond to reality. And then they can try to adjust, see there are new ingredients missing. So I know they have been working in the past years on a rotation that changed definitely the shape of the convective pattern. For me, something that rotates with a period of 30 years, I was thinking that it has no effect on the convective pattern, but it has. And now, right now, they are working on incorporating the magnetic field because it's very weak. It's about few Gauss for Betelgeuse, and it's the maximum few Gauss. But it could be the resultant of an average on the surface. And the idea would be to see if the convection triggers local dynamos that change in a feedback way the shape of the convection. I have no way, and they have no way what that would be the result of this, because it's feeding on itself. But I think we have to go this way because there are clearly observables that are absent from the current simulation. So we need to try the ingredients that are at our disposal. I know they are also looking at seeing if there is a nearby companion by a tidal effect could affect the convection, but then you can imagine plenty of configuration, even while the light curve look a bit the same between red supergiants.
On the study with the environment of evolved stars with ALMA and the top companion. So you have studied 17 stars. Sorry. What is the most important next for you? Is it to increase its statistics, its number, or to have a more precise observation for some cases, as you showed for one of them here? And at which time scale? Do we have to wait for a habitable world observatory to know more about this? Or I hope so. I guess we can do many other things in between.
Yeah, particularly when we don't know what NASA is going to do next week. So in 20 years, it's difficult. So when you say one or the other, is it exclusive, the or is it inclusive? Because ideally, I would like to have indeed a larger sample. Because we know that the atomium sample is biased. So because we targeted stars that are visible with ALMA and with the VLT, without realizing it, we biased the sample towards a high mass HGB star. So we like to go towards lower mass to see if the stars have so many companions also. And indeed, I would like to look at some of the atomium stars in more details. So I have my short list, and I already have observation with Pioneer on several of the atomium stars to look for the companions. And I can say that we find some of the companion in the Pioneer data. So it's something really I would like to do. So when I mention characterizing the companion, it's not just is it a white dwarf? Is it a main sequence? Even if it is super interesting. But in that case, if you want to understand the shaping of the environment, we need to characterize the orbital solution. So the separation, the eccentricity. So we need to repeat the observation to compute the orbital solution. So I think that's towards what I am leaning. So lower mass star and more detailed and monitoring to compute the orbital properties.
Okay. Maybe a very last short question. What I already discussed with you a bit earlier was about because I'm also very involved in Gaia. I asked you the question, why don't you use Gaia parallax? Of course, for the brightest one, you cannot get them, but for others,
for my one group, I use the Gaia observation. That's why I use the Gaia parallax and the Gaia proportion. So when it is available, I'm using it. But unfortunately, particularly for the red supergiants, because I'm studying the brightest and the largest, it is not available. And it's a big problem, particularly for Betelgeuse. If you look at Betelgeuse, every 4 years, there is a new parallax measurement that goes out from the radio domain. From last time it was from pulsation models. So they look at the pulsation and say, the star must have this size, so it is at this distance. So we don't know the exact physical size of many red supergiants because of this. So when it is available, I'm using them, the Gaia parallaxes. There is also a correction that has been published on the Gaia parallaxes from the Swedish team, mainly for AGB stars, not for supergiants. And I'm doing that when it is available.
Okay. Okay, thank you. Thank you very much. I might take more time.
Thank you, Céline.
Thank you very much, Céline. We will now move on to Fabien. So I will switch off, or maybe you can switch off your mic, Céline, which is done.
Hello. Hope everyone can hear me. So first, Miguel, let me congratulate you on a great job you did on the presentation. So you were one of the first to pioneer the multi-messenger RSG and AGB observations. I mean, I really like the example that you gave about comparing interferometry results with the LSD reconstructions. And I think that was on slide 22. And in fact, the agreement is even better than what you showed, because I think we tend to flip the interferometric images. Was it on slide 22? Maybe it was. Yeah, that one. Sorry. Yeah. So if you flip the x-axis, you see that the spot falls exactly where this is. So my first question is, do you think that the future lies really into the data fusion? So by this, I mean that interferometric observations are actually quote unquote expensive. So it takes a while to go there and do them. While I assume that LSD can be done pretty much continuously, or you can do it at several observatories. And so one could imagine having a few observations done with interferometry intersped with LSD observations so that they can tie it together. And then you do data fusion. So you have a global reconstruction process that uses both the interferometric data and the data fusion, and maybe even light curves. And even maybe speckle imaging, even though I think on Betelgeuse you get only 3x3 or 4x4 pixels. Would that be something that you would you would see possible?
So definitely the LSD and the interferometry, I think we could do it. Having a large data set over time and performing time-dependent image reconstruction. So we have already wavelength dependent. So you are talking basically about this. So having a time-dependent image reconstruction with continuity between the epoch, that would be great. Including the light curve, I have difficulties with that because what we don't look at the same optical depths with the different observations. So here in the edge band with Pioneer, on the left side with the CE theory, we look as close as we can from the station. So we are close to optical depths of 1. With spectropolarimetry in the visible, because what we look is a depolarization of the continuum, we can also consider that it is optical depth 1, or at least very close. When we look at the light curve in the visible, even if it's the visible, but that's the light curve, it's not the polarized light, then we are much higher than that. So we see molecular lines because the visible domain is dominated by plenty of molecular lines, particularly TIO. And we are way above optical depth 1. And there was the paper by Bernd Freytag last year or the year before, I don't remember, showing that we cannot do that. Basically, the two optical depths are relatively decorrelated in the sense that we cannot recover the structure. And if we start to feed the reconstruction code with information from different depths, I don't think it will work. So if we want to do time reconstruction, we need to have a consistency in the optical depths at which we are observing, which is the most critical point. Otherwise, I totally agree that would be quite exciting to do that.
Okay, so since we're talking about the temporal evolution, I mean, you've already mentioned that there are several issues in terms of spatial frequencies with the hydrodynamical models, especially the shape or the size of the convection cells. You said that the data seems to fit better with smaller convection cell. So obviously that's kind of a problem for training future generative models. So if you have no clue what things are looking like, it's going to be pretty difficult to come up with some training set. So if you look at the models, can you just rule them out from just light curves, or is this maybe the mass? I'm talking outside the large mass loss events. Maybe we could check whether dynamical evolution is the same from data, even if we don't have full resolution on Betelgeuse, or is there a way to actually do very low resolution image and try and understand what's happening in terms of temporal evolution, compare this to models?
Yeah, so I'm also very into temporal evolution. So for AGB stars, I think the models are quite good. They are managing even to reproduce the mass loss. And we see these pulsations. I've shown that in the movie. For Red supergiants, it's more problematic. If you look, you can produce a synthetic light curve from a model, any model, and all of the models. And you can see if you have the characteristic periods. So we have the fundamental one, the principal one, and the long secondary period. If they are present in the model, and they are not. When we look at the models, and I think we see it also in the movies, the light curve is not even semi-regular variable. It's totally irregular. So I think there is indeed something missing that may be related to the way waves are propagating inside the simulations. I think perhaps the MESA model are too strongly relying on proper mode propagating inside red supergiants, because they are not perfect oscillators. But on the opposite side, you have a radiative hydrodynamics model that don't have the wave at all propagating, and that seems to be what we see on on the light curves. That this component is also missing, in addition to, as you mentioned, the structure and so on. So indeed, training, and it depends. With what you have produced and that I have shown, that you can train a model with rectangles and still recover YSO. It seems that the way you train, at least for YSOs, the network does not matter so strongly. Why? So perhaps we could still reconstruct images, decent images of red supergiants with the current model, meaning that it will initially guide the reconstruction towards the star. But what is happening on the surface of the star will totally depend on the data and not on the training. At least you can try.
Mm-hmm. So I guess one could also imagine we could create empirical models about spatial frequencies from the real temporal data. After all, we do get real temporal data, and we know this corresponds to changes on the surfaces. So maybe this would be possible. Anyway, my next question is.
I would do this in the edge band. We need a light curve in the edge band instead of the V band.
Exactly. My next question would be, actually, maybe speaking of V band, what are you expecting from interferometric imaging in the short term? So in the, let's say, in the next 5 years.
Well, first, in the next 5 months, I expect that we will use the 7th telescope at Shara to obtain images of big stars again, because we cannot, because we have, we have the same at home. I hope we will be able to observe Museb, Recherches, Montarges. I think is definitely too low, but CITORI, and you have more telescopes than the VLTI. Montarges is producing images quite easily, and we could also combine VLTI and Shara data on those stars and see if the limits we try to reach are reached the same way with both facilities. So that's definitely something that I really would like to do. Moving towards the V band, for what we want to do, it's not the priority, I think, for red supergiant and LGB star. It could still be useful because it could bring us information about the TIO lines, the way they play in the opacity, in the visible, and seeing how different the contrast is between the visible and the infrared. I think it's quite different. I think we would not recognize probably the red supergiant taken with the same pattern at the same time in the visible and in the infrared. And we need to check if the simulations are able to reproduce this. But my main objective would be to increase the number of telescopes for Shara, because it's easier at Shara than the VLTI, unfortunately, to have a better UV coverage, because that changes everything. If we want to have images and longer baseline, I know there is this project of Miguel facility at Shara. Yeah. I don't know if it is compatible with having a joint US-European project in the coming decades. We have a few monies, but having longer baseline and still the capability of having short baseline and doing what we did with Montarges, 16 lobe of visibility, pushing the models to the limit, I think that's the key. If you want to understand the mass loss mechanism. Mm-hmm. The visible, I would use it for the companions, because the problem with the stars, normally when we look for exoplanets, we go to the infrared. For finding companions around the coolable stars, if you go to the infrared, it's where the star is the brightest. So we need, on the contrary, to go toward the visible to see how the companions are interacting. Okay, so my last question is actually going to longer term. So imagine it's 2029 or maybe 2030, and you now have the first images of Betelgeuse from the ELT. So what would be the next step? Well, more images, obviously, different wavelengths, expanding the sample. The advantage of the Yeti, it's a 39-meter telescope. We can do plenty of things. So we can do looking at smaller stars with more details than we did in the past. In parallel, there is already the Vera Rubin Observatory working. We may have access, I'm not sure, there are different things about it, but if you can have access to the light curve of cool level stars and see if we have the same kind of periodicity, perhaps shorter variations also, could be interesting, and perhaps use also the light curves to find companions. I don't know if that makes sense, but that's something we could definitely try on a larger sample and see if the population of companions we see in the evolved stage correspond to what we see on the main sequence or earlier stages.
Yeah, you did show the entire sample of red supergiants and AGBs initially, and there's a lot in there.
There has been also the first image of a red supergiant outside the galaxy by Keiichi Onaka. So we can also see, well, M31, I'm not sure it's exciting, but the Magellanic clouds with a different metallicity, we could prove there the effect of metallicity on the convective pattern, on the mass loss rate, for example, on the frequency of companions. So well, there are so many parameters to study, it would be very exciting.
Yeah, I guess even nowadays, maybe one could even envision a speckled survey to study companions of AGBs or red supergiants.
Well, I do that, I don't know where to do that.
Gemini, I think we could do that fairly, or LBT also would probably work. Well, that was my last question. So thank you very much, and congratulations again on the presentation.
Thank you, Fabien.
Thank you very much, Fabien. Anna, do you want to carry on with the questions?
Yes. So I'm very excited that you asked me to be in this jury, because I've been looking at your application files for some years before you got recruited, and I was really pushing you and really supporting you from there, where it's a difficult way to support you. So I was very happy that you got recruited, and I'm very happy that you show it was a great choice for the community. And you've already been involved in the supervising lots of students, which is great, and which already shows that this should be just a formality, because you already showed that you have the ability to direct researches, and also in great consortia, as the Atomium Consortium. So I wanted to congratulate you for everything.
Thank you.
And share the joy to have you in the community. Thank you for the presentation. It was super clear. I was a bit, how would I say, a bit surprised by your manuscript, because it was just like storytelling, which is a bit different from the usual research manuscripts that we read. And so it was a nice way to put your research in perspective. So I think it was nice. And I have a few questions. One maybe in line with the ones that you had just before is you are very, it's a great expertise that you have developed targeting the many regions from the photosphere up to the large CSE. And you showed all the different facilities and techniques that you try to gather to really have a complete picture. I was wondering if there's, to your point of view, any physical process, anything that we cannot probe presently with the different facilities that are at hand?
Yes.
And which ones, and what would be your wish list? And do you think that it's something that will be solved in the coming years?
So there is all this interaction with the companion, which is relatively recent. So for AGB stars, it's mainly with Atomium that we realize that we are missing the way AGB stars are interacting with companions. Wind of AGB stars is interacting. And something, perhaps it's because you are asking the question actually, and I realized, so for many years, we have been neglecting the magnetic field in the way we trigger the wind of red supergiant, because we said it's only a few Gauss, It has been measured, as you know, at the TVL, and we say it's nothing, so it cannot play a role. But what we've been saying, and I remember discussing that already with Michel Aurier, is that what you measure is the integrated field. So if we have convective cells with different polarities, like in the sun, for example, the resultant could be relatively low. And but so on such big stars with so many cells, locally, the magnetic field could be important. And we have no way of measuring that currently. And so I'm not an expert in Stokes V at all. It's something that I'm avoiding each time I can. But I don't see clearly a way to have spatially resolved Stokes V measurements. And I think we would need that, to have a map of the magnetic field of a red supergiant, and then bring that as a constraint. If we see that peculiar regions, so the intergranule, for example, or the bright part of the granules, play a role in establishing the magnetic field locally, that would have large consequences for triggering the wing. But there is no point of modeling that now because we have no way of testing it. So finding a way to test it could be quite a challenge. And then the companion. But then if the star is magnetized, can a magnetized companion play a particular role? Then that's become extremely complex. And I hope not. They are not playing an important role.
Just following up on what you're talking about, which is the companions. So you showed that in the atomium, it was HV source that you targeted. And you said that you really want to investigate it for red supergiants, where it's difficult or not known. So what would be your strategy, actually? How do you think you can really hunt down these companions? What would be the best instruments, or, yeah?
So I think the best strategy, we cannot reinvent the wheel. We have to use a strategy developed to find exoplanets by imaging, because radial velocities are excluded because of the motion of the photosphere. Proper motion, for the same reason, it's impossible because the photocenter for red supergiant depends on the convective cells, so you cannot properly define the astrometry. So I think we have to use, and also transit makes no sense because of the variation of luminosity. So we are left with direct detection, which is the worst case. So what has been done, speckle imaging at Gemini, could have worked. But what they found is much brighter than what we anticipated. So 2 orders of magnitude brighter than the predictions for the companion of Betelgeuse. So perhaps there is dust around, plenty of things actually, if it's interacting. What I did not have the time to mention that the companion they found is a pre-main sequence star. So it's a star that is a bit more than 1 solar mass. And Betelgeuse, the primary, the red supergiant, is 8 to 9 million years old because it is on the red supergiant phase for 15 solar mass. And in 9 million years, a sun cannot form. So it's still a cloud actually that is contracting, and there are no nuclear reactions inside the companion. And what is even worse is that it will probably never be, because it will be engulfed or spiraling toward Betelgeuse before even starting nuclear reaction. So in 10 years, I've imagined several times what could be a companion around Betelgeuse. I never considered this, that the companion could be a non-born star, basically, that will die before even being born somehow. So pretty sad, but that must have an impact, the way the star is forming, the fact that you have a structure that is, well, probably accreting material, shaping the wind, and perhaps tidally interacting with the star, must play a role. And something that is particularly troubling for red supergiants is that the great dimming, something that we never mentioned or discussed anywhere, is that the great dimming happen at the minimum of the stellar pulsation. So the 400 days pulsation period when the star is the dimmer. we don't know why in general it is the dimmer, but it was the dimmers at that time. And it was a coincidence of the minimum of the long secondary period. So supposedly when the companion was behind, which makes actually no sense. So there are plenty of unknowns here if the companion is real, because it's under this assumption of what a companion could cause to the light curve, to a mass loss event, because in this frame, if the companion is real, for me, the dimming has to be linked with the companion, because the period corresponds, but I have no clue how. And then finding them, as you mentioned, so Sphere for Europe, Gemini for the US, and for now, that's all. On a longer term, the ELT, I have serious doubt, because we don't have the contrast in the infrared for that. So I would say what I told Fabien, perhaps if we manage to observe a red supergiant with SHA in the visible, that could do the trick. But what I did not mention with Fabien is that for me, it's much more difficult than the infrared, because in the visible, the resolution is much better, meaning that to track the fringes, it's going to be a small nightmare. So if we manage to resolve the instrumental problem with SHA, if not with Gemini and Sphere. But again, it's not interesting. Yeah, it is recording. It's not interesting to just do that on Betelgeuse. What is interesting is to do it on many stars to try to understand what's
maybe two small questions on that point, especially, and looking from a more modular point of view, which is mine. Actually, well, I mean, you explained in the very first slides that red supergiants are very complicated. Actually, it's a very poorly known phase of stellar evolution, and it can be the second to last phase before explosion, but it can also be something en route for being blue again and red again and blue again. When you do models as I do, it's just like sometimes going back and forth, and you say, so the few stars that you can actually observe, we don't know on which of these branches there are. Is there the first time they're red? Been there blue before, red before? Do you think that there would be, by any chance, I guess, enlarging the sample of the red supergiants and to see the diversity? But do you think that from observational point of view, there would be some things that could help just constrain this evolutionary phase, because we actually don't know, and we really crave for data.
So for many years, I've heard people saying in conferences that normally the chemistry on the surface should show something, but I'm not doing spectroscopy, but it seems there has been no result on that side. So it seems more difficult than anticipated. There has been a way, I think I show it slightly at some point. It's very well, yes. This image, this one must be from ISO, I think. And we see the arc of shock, the bow shock of Betelgeuse, and something here. And that has been puzzling for many people in 2012. What is this stuff? And there were two hypotheses. This could be the edge of an interstellar cloud, and Betelgeuse is moving this way toward the cloud. Or there was one paper, controversial, but never confirmed, never totally inferred. This could be the blue giant wind. So that here we see the faster and denser red supergiant wind of Betelgeuse that is going to collide with the blue giant wind bow shock of Betelgeuse. So perhaps if this is true, I'm not convinced, but that could be a way, if we see that the star has been oscillating between blue and red, if we take a step back, which is something that your neighbor liked to say, we could perhaps see the different winds coming from different phases of evolution. That's the best way to do it.
Very last question. You have lots of projects, which is good because you're new, so we hope you have lots of projects and already a PhD direction coming in. So congrats for that also to your students.
She did most of the job until now.
And so in the coming years, among all these projects, if you would have only two PhD fundings, what do you think would be the really crucial things to unlock strategical advances?
Well, the AI reconstruction for intervention, because it has implication for plenty of other things. And also, I am biased because I know that Lucy likes that, so that counts. And I think the companions. So there is this question of the companion that is emerging for the AGBs, for the red supergiants. And it's not just finding companions for the pleasure of, oh, there is a companion. It has implication for understanding the current evolutionary status of the star, the past, how it got there, and what is going to become. And is it to become a binary compact object that's going to produce gravitational waves? And also, we know that many stars, most stars are in a binary system. The sun is a bit not an exception, but is not in the majority. So we know that the current chemical status of the galaxy results probably from the evolution of binary systems. So looking at the population of a binary star, I think it's in the evolved stage, I think it's definitely interesting.
Thank you.
Okay, thank you very much. Do you want to carry on the discussion?
Yeah. Also, from my side, congratulations, Miguel, with the vision that you laid down. I think in your document you partly look back, basically to tell us where you're going to start building from, and then you look ahead. Yeah. And so my questions are in line with what the others have asked, because we are all thinking like the future, more into the future than into the past. And so, so I have several questions about that, which I'll ask in a minute. But first, I have a tiny question. In your research field, is theory ahead of observations, or are observations ahead of theory?
Depends, I would say. So I would say that for the onset of mass loss of red supergiants, so the stellar surfaces, I think observation is ahead of theory. But on the other side, for finding the companions, we know much more about population synthesis than we know about the binary population of cool-level stars. So there, on this side, we are behind in terms of observations compared to zero. For the dust formation parts, I think we are pretty much at the same stage. We don't know where to find the first dust grains. We don't know what they are. Observationally, we don't see them. We don't see the first depletion of the gas. We cannot say that these gas species are being depleted first. And simultaneously, the chemical network has difficulties to produce the first dust grain and cannot tell us, you should look. So we know that it is SiO, silicon, that is silicium, that there is oxygen, but precise building blocks is not clear. So I think here we are on advancing together.
I thought you were going to say that, right? It was a complicated question. But in any case, more observations need to be done. Yeah?
You always say that.
And you always say that. And so I listened very carefully to what the others asked you. And so we need more and better observations. And so my questions actually are, how many new observations do you need to be able to do transformational science? Yeah? And so I can think of two directions to go. So I have two questions about these directions. Yeah? One is we use the observatories and the instruments that we have now so that we can start immediately. Yeah? That will be my first question. And the other is that we're going to build something. Yeah? Something completely new that is going to answer our problems and questions. So what everyone so far has directed you towards, is, if I understood it correctly, is a a large sample that you homogeneously analyze in multi-wavelength, in multi-techniques. Yeah, and unbiased. Yeah? You yourself said it has to be unbiased. Yeah? Maybe we should. So my question is that feasible now? What should that sample be? Should you define that sample on the basis of instrumentation that is going to come online decades from now? For instance, ELT instrumentation, Mikado or Matis. What is that huge program that you are going to lead, that is going to allow us to do transformational science?
Difficult question, because with angular resolution, the numbers is not the strength, it's the details. Because as I have shown at the beginning, in terms of red supergiants, we don't have a lot of choice. If you want to look into, for example, triggering the mass loss of red supergiant, if you want to look at the details of convection, well, 1, 2, 3, 4, well, let's say 10 to 20. But we can, if we go for interferometry, that's a huge number of hours that we will never get. So we have to be careful. But already, those two, this one and this one, the largest one, the closest one, the brightest one, are quite a challenge. This one has a very well-known companion far away. This one, question mark. And they are both similar. If you look at the light curve, the magnitudes, everything, the two periods, so the fundamental and the long secondary. And yet, the environment are also looking the same. The way convection happens here with large spots that are persistent, the great dimming, it's very different from there. So at a distance, very similar. They have every reason to be similar.
That means you need even more, right? Because the third one is also going to be.
Yes, no, the rest, we can align them more with Montarges. I think something that I've been realizing for many years now, this one seems not so typical in the population of red supergiants. So perhaps we have been studying the wrong star. It's the easiest to study, but perhaps it's not representative. There might be perhaps what Anna said, that it's coming from a blue loop, or there has been a merger or something that is changing what is happening. But otherwise, when we already look the light curve, the periods, and the convection, the other one are perhaps similar. But then we are faced with the problem that every interferometrist known in this room is that as soon as we start to study a star with the detail of high angular resolution, it becomes peculiar. You cannot put it in a box with all the other, because there are so many details that you realize that all the hypotheses you made to put them in the sample box are not working. That's what we saw with atomism. So it's very tempting, and I know that we are moving towards this, to have large samples, but it's okay when you don't have a spatial resolution. But when you have spatial resolution, there is always something where you break a symmetry. That's the problem, because you have a companion, because you have a magnetic field, you have something breaking a symmetry, and your star becomes not almost unique, I would say. So perhaps then the point would be to look at the stars that are accessible with high angular resolution. Not so many, but already a certain number, to see what is breaking the symmetry. Is it magnetic field? Is it binary? Is it both? Or the association of the two? And then understanding how breaking the symmetry in the flow of the environment changes the fate of the star, because I think it does, and the way it enriches the galaxy. I think that's the.
Okay.
If I need to summarize everything that I'm doing, the three questions in one single question, that's how to break symmetry. That's what we do in angular resolution.
Okay, so that's something that you can start doing and continue doing right now. And then my second question on this observation is, if this committee would give you a pot of money, like a big one, yeah. So are you going to do with it, build with it? What is the breakthrough thing that you need, which it will only be online, I don't know, 10 or 15 years from now, I guess.
The discussion that Guy launched me already towards a few days ago, there are perhaps two things that are linked, that are a variation on the same project. The current difficulty and the limit we have reached when doing, if we want to really image the surface, is that we get one image per year. And we know that the surface is going to evolve on a scale of weeks, months. We have seen it with the dimming. Really, together, actually, we've been seeing the image, and each time it was different, even after 3 weeks. So we need to be able to have a better sampling of that. And that is not so easy. That means having 12 telescopes, imaging a bunch of stars, like every evening, we get plenty of baselines, and every night we change a star. So we call it the telescope with Narzia Nugu, that he was the first one having this idea of putting 6 to 12 telescopes on a ring and pointing the ring actually toward the star. So you don't have delay lines between the telescopes, and you get an image of your star every night by following it. This, or perhaps a real interferometer dedicated to imaging, because the beta telescope can be only used on bright targets, small aperture, so easier to do, but more focused science, so less budget, so balance. But having an interferometer that the goal would be an ALMA, an optical ALMA, basically. That's something that I would like. So capability of imaging and spectral diversity, because clearly there is, we cannot mix observation taken at several optical depths, and we cannot mix observations taken at different time, because we blur the image.
Okay, so sounds very expensive.
Yeah, you asked me expensive.
There's another thing that is like completely new in this field, and that is the role of metallicity. And so we explained it a little bit, and that you should go to the LMC to study. Now, I agree with you for the red supergiants, yeah? Because red supergiants, you know, the youngest one is like 5 million years, and the oldest one is like 50 million years. Yeah? So they're full formed now. But for the HEB stars, that's different, right? The youngest one is like 50 or 100 million years. And the oldest one, the one that evolved from a 0.95 solar mass star, according to that is 10 gigayears. And if you look at galaxy evolution models, for instance, the Kobayashi models, yeah, then the metallicity increases more or less linearly as a function of the age of human. So by going down to lower mass, initial mass stars that are now HEB stars, you probe an enormous baseline in metallicity.
I must admit that when I spoke of metallicity, I had mainly in mind red supergiants, their convective pattern, and their companions, because I'm sure that the metallicity will have an impact on the population of companions, initial mass of companions, and how they behave. I've not thought of metallicity in terms of HEB stars at all, because there, I'm not sure what it will change clearly on the way they are forming, evolving.
But it must change things, right? Because dust nucleation depends on metals.
Yes, but they are also producing their own elements to produce their own dust. So the dredge comes from something that is already in the core of the star. So I expect, wouldn't it change mainly the initial mass distribution of the stars, and again the companions also. So if indeed we have companions interacting with the wind, depending on metallicity, it will not be the same. And the pathway to dust formation. But then, since we have no idea what is the current pathway for dust formation at the current metallicity, even more. So,
But my point is that, I mean, it's already in reach for HB stars. Yeah.
depend on the brightness and
Sure. Thank you.
Thank you. Philippe, you want
Okay.
to carry on?
Yes, first I want to thank you for inviting me for the idea, because as Anna was a fan of your work since the beginning, so I'm really happy to be there today. You have done a very impressive work of coordination, not only of instruments, but also of people. It's really a proof that, or evidence that research is a teamwork, really, and it's very impressive for me. You did not mention all the other things that you are doing during the day and the night. I don't know how long you are sleeping during the night, because you are proactive in many fields, especially, for instance, you repaired the refracting telescope in this building. It's something that you are doing and working with amateur astronomers. You didn't mention, but this is.
I did not do it alone, repairing the.
Yeah, I know. So again, it's teamwork and all the work you are doing, but this is something that takes time. So congratulations also for that. Coming to at the end, most of my colleagues have already asked all the questions, but I still have few of them. To summarize, because you have made a very nice teasing of your work, but you ask how do you start the mass loss? And I think at the end of your presentation, we still don't know. It's a good.
There is still work to be done, definitely.
It's the same thing for the dust formation. As far as I understood, it's not really clear how you can form dust, especially on slide 45. You mentioned that you just mentioned it, that you can form a dust very close to the star. But have you some idea about physical processes that allow dust to form so close? Do you have an idea, for instance, of the temperature at this distance of the star?
So we are close to the 2000. So that's the difficulty. So when we did the paper on the great dimming, there were radiative transfer simulation behind in 3D with radiative 3D, and we have some ideas where to put a clump of dust to have observe what we observe. And we were in the region just below, if I remember correctly, 2000. So it's quite hot. So to have dust, you have few species that would work. There's alumina precursors, this kind of stuff. And but when you look at the pathway to form dust, it's not normally there that you would go to have the first grains. So there are some contradictions. That it's not so easy to grow dust species there. So the physical process exact, I don't know, and I think it's not clear. Forming dust far away, it's easy, the big clouds of dust, but really the first grains there, basically, that's the trick. And we have yet to identify precisely the species, because basically when behind these images, this one produced by Emily, so there is a radiative transfer code, so that was a MC Max 3D, and behind this we have to get the optical properties of dust that are obtained from experiments in labs, so the optical constant of the species, or sometimes from what is observed on the sky. But here we are dependent on what is given to us in the databases. We don't have access to all the dust species, the dust precursors, and also the configuration of the species, because the way they are, the monomers are oriented, changes the optical properties. So it is definitely possible that we are exploring the range. Also, it takes time to produce this, several hours, because you run a grid. So you cannot explore all the compositions and all the properties that are in the libraries. So perhaps the answer would be there if we had an infinite amount of time to run simulations, or if we had an infinite amount of material and time to run laboratory experiments. So that's quite tricky. But definitely the process, no. I know that we have people like David Gobrech, who has now left academia, if I remember correctly, was working on chemical network to start from monomers to clusters of dust.
Because I'm more familiar with more massive stars physics, but maybe you may have some non-LTE process as well. Or, I'm sure we don't know in this code. I mean, it's LTE, no?
Yeah, it's yeah, because we have to make an assumption that there is a T. Okay. Because the code it's a static, so we put a cloud there with a given composition, and it's not feeding on itself or changing. So it has to be a T.
Okay.
Then we would need, for what you are leaning towards, coupling hydrodynamics with chemistry and radiative transfer. So we are starting to get the hydrodynamics of the gas and dust when there is a companion, but coupling that with chemistry, that's a huge step.
I have another comment, yes, maybe about the slides 35. So I was a little bit surprised by, yes, the first thing that the first image, reconstruction by squeeze. I'm just surprised that you can find smaller structures that are smaller than the beam, on the first image. So it's, well,
it depends on the definition of the beam always. I don't remember how it was in this paper, if it is lambda of B or lambda over 2B.
Okay.
But also when you have something that is well resolved this way, so normally the beam will fall somewhere like at the zero of the first lobe or the half of the first lobe. But if you are well resolved, actually you can get much better detail than that. So.
Okay, and in the same idea, just if you can go back about the detection of the companion or Recherches, the image. I must mention that I'm really not in favor of this conclusion. I mean, the burst that our US colleagues are made about this image is huge compared to the signal to noise that you have in the image. I mean, I'm working on a massive stars image reconstruction, and I can have 100 of companion around massive stars because 1.5 sigma detection in an image is not the same as 1.5 detection on a spectra or polarimetric signal. I mean, I do not believe at all about that. Just my point.
Well, so I try to be politically correct for the past 2 hours and destroyed everything, but I agree with you. But that's not the worst. For me, that's really this the worst. Because
sure.
Here, the problem on this image for me, that of course, there is something missing here compared to the other stuff. But no, the real problem, if you zoom in, you see that there is an elongation of the primary toward the companion, suggesting that the primary is somehow feeding the Roche lobe, so that there is an interaction. And initially, for the first 12 hours, we had for the first day, actually, we had only this image. And for me, when I saw that it was feeding the Roche lobe, because I saw that it was the real image, okay, it's real.
Yeah.
Even if this detection is weak, the fact that the primary is feeding the Roche lobe was okay. But when we got this, and actually I got this before anyone else because I got a private message and I got it the same evening than this. And I was, well, I'm not going to say what I was, but there is no elongation of the primary towards the companion. So this is an artist license. So yes, this is bad. This is bad, and this is above what we would expect for the predicted companion. So I think, well, we need to compare with our own observation, but I don't think we see anything, but perhaps we don't reach the appropriate signal to noise ratio. So we need to wait for 2027 to see if the companion appears on the other side, and if in the meantime there is also nothing. Because if we see the same thing this winter or next winter, then I mean that it's irrelevant. So we more observations.
Yeah, that's a good conclusion. Yes. Just about, yes, we already talk, Céline and Anna talk about Gaia, but I know that it's a complicated thing to get the parallax for the stars, because you have to take into account the convection, because the parallax is as accurate that you should not take into account mistakes. But I'm sure Gaia detected many more RGB, no? Because when you show the HR diagram, observe HR diagrams, there is more.
Which one?
The first at the beginning.
But that was just
before Gaia, no?
Yeah, it was just an impression to feel to give name to stars in the introduction.
Okay.
If we look at Gaia, we have much more.
Okay.
But the problem with those, there are red supergiants and HB stars, because of course if you look far away, the convection becomes less important than the parallax. The problem for the stars I am interested in, well, those two for the red supergiants, is that the parallax is smaller than the angular diameter of the star. So you try to measure a photocenter displacement over the disk where you have all the convection. So impossible. So the problem is for the nearby stars, which are the ones that we can observe in details.
Okay. And maybe just two last things in your manuscript that I really appreciate. There is two chapters that you did not mention in your presentation.
We didn't have the time.
Yes, but you have the opportunity to say a few words about the sustainable research pathway that you wrote in your manuscript that I found very interesting, and about the consideration on teaching as well, because you have teach a lot. So if you can say a few words about these two aspects.
Well, for the sustainability, I have the feeling more and more that we are really running towards having results and metrics of paper, even if we claim in conferences otherwise that papers, the number of papers are not counting in the end for the ERCs, for the ANR, that counts, and we are all running for those fundings. And simultaneously, we see, perhaps because I have more seniority also, I see more and more mental issue problem in academia, not just in France, but worldwide. We have more and more, particularly for postdocs. I know particularly well how difficult it can be to combine having a private life, work life, and running for a permanent position. And there have been efforts for that. But we are still, I think, far from a sustainable pathway in this sense. And we are doing astrophysics. So it's important, we like it. There is a competition, there is public money involved, so we have to be to deliver in the end, but perhaps not at the cost of well-being of people in the field, and not just researchers. It's also true for administrative people, engineers, and we all know that there are quite some difficulties worldwide, and particularly in France and in Paris Observatory on that field. So and just saying this sometimes I think that in conferences we have plenty of goodwill toward this, and when we are back in the laboratories, okay, we have done it, we put that behind, and we continue as usual. I disagree. And there is a slide I prepared and did not show in the end. It's not even in the PDF. I did my CO2 budget over the past 15 years, and it's impressive that. So I plotted the trains and the planes travel, and basically you do not see the train. You have to put a log scale to see the train. So when we think of CO2 budget, well, it's the plane travel, even if it's for a large institute, it's negligible compared to buying goods, for example. It has a weight. And when I did my PhD thesis in this room 11 years ago, the effect of climate change, we were still thinking that they were far away from us. That when we were fighting climate change during my PhD, it was for the future generations, for our kids or our grandkids. And now in the past years, we have realized that no, it's for us. We've seen it here in Paris Observatory, when it's 40 degrees outside, in our offices, it's impossible to work. We have to take refuge in a cool room. While that was not the case 10 years ago. We could work in our offices all the time. We have thunderstorms that are more important, and I think we need to do something, each of us, and each time we think, oh, but others should do it before us, it's trying to find a way not to do anything. Your neighbor has a nice phrase about it, is that our mission as staff is to conduct research in astrophysics. We are paid for that. So one of the solutions, of course, would be we don't do anything anymore. And then we do not emit CO2. Even if we are not in the building, we do not pay electricity, and that's less CO2 also. But no, that our mission is to do astrophysics. So we have to conduct our work. And we have to find the best way to conduct our work. And I am convinced that seeing the models, the observation, the instrument that we can use, so that we can find a better way to do it. So continuing to do astrophysics in a way that is sustainable. And about teaching right now, after 2 hours of talk, it's more difficult. I don't remember what I wrote in the manuscript actually, but yes. That's something that I found is missing, perhaps a bit less now than 10 years ago, is training of the teachers. So as researchers, we know how to do research, we know the physics, astrophysics, we know numerical stuff, but how to transmit this to students and to evaluate it also properly. It's not, you cannot know it by yourself. And that's we begin to have training sessions. It's not yet mandatory, at least in Paris Observatory. It's mandatory for the maître de conférence, but for the CNAP, it is not. And yet it is quite interesting. And I think it is important to find good ways of teaching, particularly now that there are new tools available that are changing the way we do teaching.
Sure. Okay, thank you.
Okay, thank you very much, Philippe. We are running a little bit late because of how many questions, so I will have to be fairly quick. First of all, I want obviously to congratulate you for the clarity of everything you wrote and the clarity of everything you say. So it is a talent that you have, and the talent that gives you the power to be much more convincing to what you say. So this is very important. And also what is, in my mind, very impressive is how over the years you have accumulated a huge corpus that gives you a fairly holistic view on the star, which is Betelgeuse. And you were very good at demonstrating how this multi-wavelength, multi-instrument, multi-methods view helps you build a full picture of a star, which shows that it is unique. And my understanding from your answer is that Betelgeuse is unique, but every red supergiant looked close enough is unique. It's in its own way. So that begs, the question is how representative it is of red supergiants, and I think that you provided the answer. You at some point I fear that you would be apologetic about being a single star astronomer. First of all, there should be no shame on that. Yes, very prestigious people have built their career on studying in a single star, which is the sun. So in as much as we have sun astronomers, we could have Betelgeuse astronomers, there would be no shame to that. But you showed that you are a multiple star astronomer, which is even better. So I have a short question about two of the other stars that you have observed at CE Tau and Aldebaran, and they are slightly connected. So if you can get back to slide 23. Yes. So this is the comparison of direct informametric imaging and spectropolarimetry imaging, and there is some connection between the two. What seems to be very different in the images is the dynamic range of the images. And I tried, of course, it all depends on how you scale it, but still, if you look at the scales on the right, on the left, it seems that the image on the left is much flatter than the image on the right. Is it an artifact? Is it something which is due to the technique? How do you explain that?
It's an artifact. So here it's an image reconstruction where we are basically, I'm exaggerating it, but filling it pixel to reproduce a Fourier transform.
Yes.
So it's really working on an image of something that is supposed to be a star that we observe. On the right, it's very different. We have a sphere, and there is a decomposition of the structures in a spherical harmonics. And intrinsically, because we use this method, they use this method actually, we have dark areas and bright areas. It's like when we try to understand the distribution of energy in the universe, or something they do in cosmology, necessarily, depending of course on the number of orders we use in the decomposition, these dark regions, very dark, are cohabiting with the very bright. And that's precisely the reason we need interferometry to recover the real contrast, because this is an artifact of the reconstruction process.
Okay, so the true contrast is rather than one on the left, or somehow.
I wouldn't go that far, but the closest to the truth is on the left, I would say.
And now I'd like to move on to the slide. I do not have the number, sorry, where you have the
16 node.
The 16th node on Montarges.
No, it's before, I think.
Which is quite impressive, because I don't think I've been any further than the third node on the star. And that begs the question, as you can see, the 16th lobe is very low. It's about 10 to the minus 5 compared to the continuum. So it's also a dynamic range issue. Is there a need? I mean, have you reached the limit of the instrument into capturing so much dynamic range between the lobes? And is there a need to go further in to improve the quality of the imaging?
So I'm going to be politically incorrect again. The problem, to answer that question, we would have needed to reproduce the observation. It has not been possible, because after this, right after this, there has been a change in Pioneer, an instrument with a change of detector. The rapid detector has been installed, and now we cannot observe bright stars with Pioneer anymore, so we cannot do it again. There have been discussions in reinstalling the old detector. They have never reached something real. I don't know if we will ever manage to recover this, but we don't know. We don't know if we have reached the limit. Betelgeuse is slightly larger, so we should have tried. We were supposed to do it, and then we didn't. So I think we had 1 year where we tried with bad weather, and then they changed the detector. So that's something I would have loved to do, but it's out of my hands, unfortunately. And with gravity, we managed to do something similar with Montarges, so that's what Lucy is working on. I don't think we've reached the 16 node of visibility. We are a bit before. But again, everything is connected. We come back to the other subject. We use the companion of Montarges. So gravity is 2 instruments in one. So we use the fringe tracker on the instrument, which is a B main sequence star that is not spatially resolved. So we can have the fringes on the companion, and we use the science combiner on Montarges. And I think Pierre is the first one who suggested that idea, and we did it, and it worked. And we can reach, I think, somewhere here. It's in the K-band, but I think we are around this region. We cannot reach there, unfortunately. But we can only do it on this star because it has a companion. We cannot do it on the other one.
Of course. But if you say, for example, if you were to write a proposal about the instrument that could be able to have a much more dynamic range into observing lobe, would you have a convincing scientific case into convincing an agency to spend some money having the right detector or the right assembly to go much fainter and going to the 25th lobe, or is it just a stunt?
I think that by myself, no. What we will need to do is convince other communities that are going to a super high resolution. So not just there, but when we go in small details, we have new physics that we have not yet explored on not just Rasupajan, but also other objects.
Okay.
And I think if we manage to discuss between communities to do that, that would work. But for cool stars alone, I am convinced it will not work.
Okay. Let's see how much time I have left. So I'll go with the final question. You showed it's in your last two chapters. You showed that you really care for education and training of young astronomers. You already not only showed it in your manuscript, but you showed it by your actions and what you did. And you made a very interesting point, which I want you to develop a little bit here. In your last chapter, you elaborate on the necessity for young scientists to keep an almost sensorial connection with the sky and the objects they observe and the instrument they observe with, because obviously our work is now mostly abstract in a way. So can you elaborate on this and why it is useful for the training of scientists?
Well, sometimes when I discuss with people, I'm surprised to see that people, they don't care where the targets are. So when we observe, I don't know, V1295 Aquila, which is the name of the young stellar objects, we have no idea where it is, where to point it, and it's like it's an ethereal object that exists only in the computer. And I found this very strange because we have the chance of working on objects that are in the physical and real world, you know, not always visible to the naked eye, not always blinking to the entire planet for a few weeks, but they are in the sky. So you go outside at night, and if you do outreach, I find it very sad when people ask you, what object are you studying? And I don't know. I'm studying an object, I don't know where it is. I find that really strange. There are, I think there is a fundamental problem, perhaps it's because I'm French and you know, Descartes and this kind of stuff. If we forget that the objects we are studying have a meaning in the real world, in the physical world, and they are there, how can we measure and quantify the, I don't know, pertinence or the strength of an observation, the signal-to-noise ratio, basically. Then you can publish stuff that perhaps don't exist, like the 1.5 sigma detection. If you don't care about the reality, it's just an ethereal object on a computer, perhaps that comes from there. I don't know. We are also living now in a world very different from when I did my PhD thesis, because reality does not matter anymore, at least for the president of the US and the president of Russia and plenty of other people. When you say, you are doing something wrong, but no, I'm not doing it. You are inventing the facts. And if us who are studying physical objects, we forget that they are a reality, I think that it has a very deep problematic way for science, for the way we communicate science to the people. And we have seen that much more than we thought, science is the base of democracy. We are experiencing it painfully every day now. And now we see that we need to be able to say, I study an object, it's in the sky, the data are public. If you want, you can check the coordinates, you can check the data and prove that I'm wrong. So, I think that's why it's particularly important. And I think also we do better science when we understand what we do. When we work with observatories that are on the other side of the world or in space, it's easier to forget there are human beings behind, working at night in difficult conditions sometimes, where you have a lack of oxygen or lack of humidity. You have to climb up a mountain. It's something that is physical to do observation, even if we are not in the secondary mirror cage anymore to put the photographic plates. When we do observation at ALMA or technicians that are maintaining ALMA, it's physical. And I remember people yelling because during the COVID, we were closing ALMA to preserve the health of people there, but because they were forgetting they were human beings before. So I think that also manipulating telescope, at least once in your career, is important to understand that it's not just pressing a button in your office and automatically, because there is an AI behind, you have data that are ethereal in your computer.
Okay.
And science is also a question of humanity and interpersonal relationship, as you well know.
Okay, that is a very good conclusion. So we will stop here for the discussion. We have to stop here because we are a little bit constrained by time. So the jury, we will move on to the deliberation room. We will come back no earlier than 5:30 and probably no later than 5:45. So for the public, you can be here back at 5:30. And so let's go and see you soon.
Thank you. Continue à parler.
Non, on va faire comme si tu attends depuis tout à l'heure là-bas.
Je suis jamais parti en fait.
Jamais parti.
Mettez-vous un autre désactivé. Ouais, comme ça, on va.
On peut avec un des vidéoprojecteurs, non aussi. Ah oui, t'as tout ça.
I have to take my notes. I think Anna can Maya, she had to leave early, so but she followed up until the end of the deliberation. So Miguel, we just heard your presentation and we congratulate you for the amount and the consistency of your work. So it seems like you have been able to pick up many pieces of a puzzle that you have been able to start assemble to develop a clear picture, not only of Diriger, but other phenomena. It was very impressive to see how clear and pedagogic your presentation was. And to us, it shows that you are really on top of the physics of this research field. That is very clear from your presentation and from your memoir. You gave a good overview of the various techniques that you use, which means that you have a good comprehension of them. And we particularly appreciated that even though you are in a very, where's my note? Even though you are in a very competitive field, you knew how to credit collaborators and students. It was very clear from your presentation and from your memoir. And it shows your engagement into collaborative work. That was very notable. You also have a well-articulated vision for the future of this field. And we believe that you have the knowledge, the skills, and the international network to carry out this vision. And we certainly encourage you to do so. And we hope that with an HER, you will have the stature to move on to the next level, like leading a major ERC or large consortium. In the answers you provided to our questions, we appreciated that you had a capacity to sometimes step aside your own work and to see its limitation or even challenge it. We thought it was very notable. One thing that we were impressed with is the project that you led on the Leonard occultations. Not only because it's you managed to take what is essentially a pro-am project, to take a bunch of amateurs and to steer the project into a research which is worthy of nature's consideration. I think that is remarkable. We'll see if that gets published into Nature, but at least that did not turn you down at the first send of the manuscript. We also noted that you are a relentless promoter of astronomy into the public. That shows, and this is very beneficial to the field. You are, in our opinion, very efficient in doing so because in the way you do astronomy with guts, you are very charismatic, and this gives you the capability to pull out groups behind you. And one more example of that is how you were able to pull a group for the restoration of historical instruments. And I think this will be very useful and very important for helping the students reconnect with the sky and the observations. So for all of these reasons, well, I think I have to say it in French. Nous vous attribuons l'habilitation à diriger les recherches de l'Observatoire de Paris-PSL et on recommande la publication du mémoire sans modification. Il y a deux catégories, une catégorie avec et modifications, donc c'est sans modification, à part peut-être quelques typos, et puis bien entendu, on approuve la dernière page qui est envoyée, qui sera incluse dans le mémoire et qui concerne l'observation du compagnon supposé de quel jeu. C'est moi qui ai un jeu de supposé. Voilà. Donc, félicitations.
Merci. I'm switching to French, but we never do some part in English still. Merci beaucoup. Ouais, j'essaie d'être rapide. Merci beaucoup, Vincent. Ouais, rigoler, normal. Donc bon, voilà, c'est la partie. En fait, c'est là la partie la plus difficile pour moi maintenant, qui commence. Déjà parce que j'avais mis mes notes pour les remerciements sur le téléphone, qui refuse de se déverrouiller puisqu'il a été verrouillé par ma jambe à travers le pantalon. Donc heureusement, j'ai tout sur l'ordinateur aussi. Et surtout, bon, je vais essayer, il y a certains d'entre vous qui étaient là il y a 11 ans pour ma séance de thèse, de ne pas faire aussi grand et pas aussi larmoyant. Comme ça devrait aller. Donc, merci beaucoup à vous tous déjà d'être là, surtout vous, les membres du jury. Ça fait 10 mois que j'ai pris mon poste, et en 10 mois, s'il y a une chose que j'ai réalisée, c'est que ce qu'on a de plus précieux, c'est notre temps. Et vous m'avez accordé énormément de temps en relisant le manuscrit, en étant là aujourd'hui, et donc pour ça, je tenais à sincèrement vous remercier, parce que je mesure ce que cela représente. Et je tenais aussi à remercier mes 2 anciens directeurs de thèse qui sont dans la salle, Pierre Carvela et Guy Perrin, puisqu'on a commencé l'aventure ensemble en 2011, et voilà, maintenant on est là, et je trouve ça formidable qu'au CA, qu'on puisse le faire à Meudon tous ensemble, ça m'émeut beaucoup. Et donc, avant d'entrer plus dans les détails, je veux aussi tous vous remercier parce que si vous êtes là, aujourd'hui, je vous ai invité au cinéma du jury, contrairement au jury de thèse, là, je vous ai vraiment choisi. En fait, vous savez que le chemin a été long, hein. Et si j'ai réussi à tenir jusqu'au bout, c'est aussi parce que vous étiez là, derrière moi. Hein, les remerciements, c'était sur la science. Ben non, c'est aussi... Enfin voilà, vous qui êtes là aujourd'hui, il y a des gens aussi qui sont en ligne, il y a Fabien et Céline qui sont là. En fait, si vous ne m'avez pas soutenu dans les moments les plus difficiles, peut-être que je n'aurais pas été jusqu'au bout de tout ça. Et voilà, plus en détail, Vincent, hein, je tenais à ce que tu sois mon président des jurys de HDR. Tu étais directeur d'Ilesia et finalement, un directeur de labo, ça n'a pas tant de pouvoir que ça dans ce domaine-là. Il y en a quelques-uns dans la salle, il y en a aussi en ligne, et en fait, non. Mais ce que tu as pu faire, c'est que je me souviens, à chaque échec, quand même, on a été déjeuner ensemble, et tu m'as dit, non, allez, peut-être que là, tu peux t'accorder une semaine des primes, et ensuite, tu continues hein, jusqu'au bout. Tant que tu as un contrat, il y a de l'espoir. Et voilà. Ça a payé. Alex, also, we have meetings regularly because we are collaborating together. And the same, you've been supporting me each time when we do not understand the decision. Sometimes you said, as long as you can, do your science, do what you like, and then you will see, and it will pay off in the end. And it did. So, thank you. And Fabien, tu es en ligne. Voilà, je ne sais pas si on l'avait dit au départ, mais tu as Atlanta, donc il est tôt pour toi, quand même. Et voilà, peu de gens le savent, mais bon, il y a eu quand même des sérieux doutes hein, à des moments. Et tu m'as gentiment proposé, plus que gentiment même, tu as suggéré que je puisse venir travailler avec toi à Atlanta de manière permanente. Alors, je suis faux bon. Je suis désolé, mais de l'autre côté, je suis très content d'être ici et j'espère que quand les choses se seront peut-être un peu plus calmées, je pourrai revenir travailler avec toi. Les séjours que j'ai fait à Atlanta, ce que tu m'as montré, ce que tu m'as fait découvrir, et puis nos discussions aussi sur plein de sujets numériques, essentiellement, ont été passionnantes et j'ai vraiment envie de les poursuivre. Et on travaille déjà avec Lucie dans ce domaine et c'est vraiment passionnant. Et donc voilà, maintenant, c'est plus personnel, des personnes qui m'ont vraiment particulièrement soutenu ici à Meudon, Vincent Lapéraire, tu t'y attendais quand même, j'espère, Daniel Laurent aussi, et avec l'aîné qui a dû partir. Ben voilà, depuis 3 ans, on a un petit projet qu'on mène ensemble sur notre temps libre et qui a débouché sur quelque chose quand même dont maintenant tout le monde profite et dont on va profiter dès la semaine prochaine. La remise en marche de la grande lunette, ça paraissait fou quand on s'y est mis et pourtant ça a marché. Et moi, personnellement, surtout 2022, 2023, 2024, ça m'a vraiment aidé à tenir. Me dire, ça vaut le coup de rester quand même, parce que sinon, faire que de la science, au bout d'un moment, on se dit, bah, c'est bon, on peut le faire n'importe où, autant partir ailleurs, autant faire autre chose. Mais ce machin-là, il est là que ici, et c'est ce qui fait que cet endroit est unique. Et donc, ben voilà, merci d'avoir soutenu le fou, là, de 5D, qui voulait lancer là-dedans. Et puis pour tout le reste aussi, il y a plein de me raconter pendant des heures tout ce qu'on fait ensemble. Mais voilà. Et tous nos collègues du bâtiment 5 aussi, il y en a ici, il y en a qui ne sont pas là. Mais voilà, c'est chouette ce bâtiment. On dit souvent qu'on a un des meilleurs bâtiments de l'observatoire, pas seulement pour la vue, pas seulement pour les locaux, mais surtout pour les personnes qui sont dedans, je pense. Et parmi les personnes en particulier à remercier, mes 2 co-bureaux ces dernières années, Irène, et Irène caché, et Nicolas, qui peut-être est en ligne, je ne sais pas, qui est tous les 2 étudiants en thèse, même Irène était étudiante en M1, et maintenant tu partages mon bureau, et ben voilà, vous avez dû me supporter quand j'avais les échecs du CNAP, en gros, mais aussi des très bons moments. Et ben, voilà, je suis content que vous soyez là. Mes nombreux collaborateurs, je ne vais pas faire la liste, je vous rassure, parce que sinon on ne va pas s'en sortir, mais parmi les personnes avec qui je travaille, il y en a 4 que j'aimerais vraiment particulièrement remercier. C'est Fabrice Serpin, dont j'espère qu'il est toujours en ligne sur YouTube, Agnès Lèvre, qui plusieurs fois m'ont dit vas-y, allez, continue, parce que vraiment, chaque fois qu'il y avait ces échecs au concours, la tentation était de se dire c'est bon, j'ai mon agrég, je peux aller faire autre chose, et qui m'ont poussé à empiler, et voilà, miraculeusement ça a marché. Emma Bourdier, je ne sais pas si elle est toujours en ligne, on travaille ensemble, on est amis, on discute. Et puis Anthony Berdeux, tu mentionnais le résultat sur Léona, mais sans les discussions et le travail d'Anthony pour la représentation d'image, je pense qu'il n'y aurait pas de résultat. Il faut quand même lui rendre honneur, et j'espère que son travail qu'il fait avec moi et avec plein d'autres personnes et qui permet que plein de choses fonctionnent vont déboucher sur un jour le fait qu'il puisse le faire de manière pérenne dans le domaine. I'm switching back to English, and so there is only one other person that I can thank in English in the room, besides Alex. It's you, Emily. You were my first PhD student. Don't do that. 2017, 2021. So I attended, well, we worked together. I miss you. I must say that I miss our discussion, working together. The great evening, we went through that together in the middle of COVID. It's easy when we see the nature results to forget that behind this, there were meetings on Zoom when we were isolated in our apartments in Leuven without being able to see anyone. It was quite special. And I really enjoy working with you, and you have no idea how happy I am that you are here today, because you come from Ireland for my defense. That's crazy. But you are a crazy person, we know that. And you have a crazy supervisor. Tous mes stagiaires, vous êtes plusieurs à être là, et c'est fabuleux. Ça me fait vraiment très plaisir. J'espère que vous avez pu voir que ce que vous avez fait, c'était pas juste un petit projet sur un coin de table pour vous donner du boulot pendant que vous étiez en stage avec moi, mais ça fait partie d'une grande aventure pour comprendre la masse des super et la perte de masse des supergéantes rouges. Et la plupart d'entre vous allez peut-être travailler sur autre chose. Il y en a certains qui vont vraiment dans des trucs complètement différents, les 2 du fond en particulier là-bas. Mais heureusement, il y a quand même quelqu'un qui va continuer dans ce domaine. Et ensuite, Philippe et la chose. Combien de fois tu m'as dit il faut jouer la partie jusqu'au bout, aussi pour ces concours. Tu nous as même accompagnés jusqu'à Séville pour raconter qu'est-ce que c'était de voir Montarges disparaître derrière les nuages. Et puis voilà, tu m'as fait découvrir plein de cibles de télescopes, ici à Meudon, à Collioure, que je ne connaissais pas. Moi, tu m'as appris plein de choses. Et ça, les gens qui m'apprennent des choses, moi, je les adore. Donc, voilà, et je suis heureux que tu sois là. Et il y a encore plein de choses de prévues. Ça va être formidable. J'ai appris qu'on allait faire l'interférométrie entre Douillac, Souperpertus et Collioure. optimiste, hein, mais bon, qui sait. Sophie Léonardon, qui voilà aussi une trace de mon passé à l'IRAM, qui était opératrice au plateau de Mur, et tu es là aujourd'hui, et ça me touche particulièrement. Hein. Avec toi, avec Émilie, Alex, tous les endroits où je suis passé sont représentés, et ouais, voilà, tu m'as beaucoup soutenu dans cette aventure, à râler après les jurys, mais qu'est-ce qu'ils font? Et tu m'as beaucoup appris aussi quand j'étais au plateau de Mur. Si j'ai pu vraiment faire de la radio-interférométrie en comprenant ce que je faisais, c'est grâce à ce que tu m'as appris quand j'étais astronome en service là-haut, parce que j'ai compris vraiment la physique de l'acquisition des observations, plus que juste, ben voilà, il y a des données qui apparaissent. Quoi. Donc ça, c'était vraiment intéressant. Ouais. Jean-Michel et Cathy, juste à côté, ça tombe bien. Ben oui, mais le festival à Collioure, sans vous, il se serait arrêté il y a plusieurs années, je pense. Et s'il a grandi, s'il est devenu ce qu'il est aujourd'hui, et qu'il y a des gens qui veulent revenir rapidement, c'est largement grâce à vous. Vous l'avez contribué à le rendre plus humain, à l'enrichir, à le développer. Et puis voilà, sans vous, il ne marcherait pas, quoi. J'en ai bien conscience. Et vous êtes là aujourd'hui, ça aussi, c'est fabuleux. Et ben voilà, vous tous, hein, parce que, comme je l'ai dit, vous m'avez soutenu d'une manière ou d'une autre dans ces épreuves, depuis essentiellement 2017, hein, c'est là que c'est devenu très difficile, mais on y est arrivé quand même. Yamina et Goran, Yamina n'est pas là, mais si on a un pot qui nous attend, premier, là, il reste quelques minutes hein, seulement, c'est grâce à elle, et Goran qui permet que voilà, toutes ces soutenances au LIRA soit retransmis sur YouTube, on me dit mais c'est incroyable, vous faites ça juste pour la tienne ou pour toutes? Je fais pour toutes. Goran, il assure ça, et même pour tout l'observatoire, tu fais des choses. Merci, franchement, t'étais pas là, voilà, ça marcherait moins bien quand même, il faut le dire. Et la toute dernière personne que je vais remercier, et j'espère que ça ne surprendra personne, eh oui, c'est Lucie, Amel, puisque si on est là aujourd'hui, c'est parce que tu as tenu à faire ta thèse avec moi. Donc il y a plein de personnes qui m'ont dit oui, passe ta HDR tout de suite, au moins tu es tranquille après, c'est fait, tu es dans la lancée des concours. Je dis oui. J'ai dit ça en mai, j'ai dit oui, je vais le faire. Et puis en septembre, à la rentrée, ça paraissait déjà moins évident de se dire rédiger un manuscrit, puis il y a toute la procédure de constituer un jury avec toutes les règles établies, voilà. Mais quand il y a quelqu'un de super motivé qui vous dit je veux faire une thèse avec vous, et pas personne d'autre, et j'avais même pas de sujet encore proposé, on l'a construit ensemble. Ben, ça motive. Et donc voilà, je pense vraiment que sans toi, on ne serait pas là. Et j'ai beaucoup apprécié de travailler avec toi pendant les 4 mois de stage. Et donc on a 3 ans. J'espère que ça continuera aussi bien, même si je ne suis pas trop inquiet. Et donc, merci et j'espère qu'on va en profiter. Et la dernière chose que je voulais dire, donc on a parlé que l'astrophysique c'est quand même important pour plein de choses au-delà de l'astrophysique. Hein, on a vu vis-à-vis de la démocratie, vis-à-vis des faits, etc. Et une seule phrase, c'est que là, on a quand même l'impression que ça va mal dans le monde. Il y a du génocide, il y a des dictateurs partout, voilà. Dans l'obscurité, ça va à nouveau, hein, comme il y a 100 ans, malheureusement, on espérait l'éviter. Voilà. Mais ce qu'on peut se dire, au-delà du fait que la science permet de s'en sortir, et un élément essentiel des démocraties, c'est que peut-être que la meilleure façon de trouver un peu de lumière dans l'obscurité, c'est de suivre des astrophysiciens. Voilà. Merci à tous. Il y a un pot qui nous attend. Et en parallèle, alors pas tout de suite, mais dans un quart d'heure, 10 minutes, on peut aller visiter la Grande Lunette. On va bien. No, we will not use today.
Félicitations. Voilà.
Merci. Voilà.